Gnanam Paramam Dheyam. Knowledge is supreme.
Recall that in the last lecture we have proved that when we have a finite field extension, then the Galois group, the order of the Galois group is less equal to the degree of the field extension, and this allows us to define a particular type of field extensions, what are so called Galois extensions. So let me define properly. So definition: a finite field extension L over K is called a Galois extension if the equality holds. The equality order of the Galois group equal to the degree of the field extension. Such extensions are called Galois extensions. So first of all, we have at least few examples. We know that so obviously the trivial extension K over K is Galois extension, because the degree is 1 and the Galois group is trivial, so it's obviously Galois extension. We have also seen that C over R is a Galois extension, because in this case the group has 2 elements and the degree is also 2. 2. If I have a finite field extension of finite fields, finite field extension of finite fields is also Galois. And in this case also we have immediate consequences. The Galois group is cyclic, both the cases, in example 1 as well as 2. So now the next is I am going to analyze when can a simple extension be Galois. So let us recall what a simple extension means and what. So first of all, recall that a finite field, in general, a field extension L over K is simple if L equal to K of x for some x in L. So remember our notation, L is a field here, it contains K and x is an element in L. Then we take the smallest, this is the notation for smallest K algebra that contains x. Smallest K subalgebra of L containing that element x. And then we have seen then all elements of this subalgebra are precisely the polynomials in that x. Now the polynomials may not have unique coefficients because it's only an element. It may not be an indeterminate. So, but now, uh, strictly speaking, we should consider K round bracket X. This is the quotient field of this, and then this also contained in L because this is a field and it is the smallest field that it contains this algebra, but L is one such, so this is the quotient field, therefore it is contained here. So simple extension means round bracket here. But why did I write a square bracket? Because we are assuming that the extension is, if we assume L over K is finite, then Kx is already a field and therefore it is equal to K round bracket X. This we have seen last time because it's a finite extension. More generally, actually algebraic is enough. If you have an algebraic extension, then whether I write a square bracket or round bracket, it is the same thing. This we have proved in earlier when we discussed about element wise characterization of algebraic elements. So in general we are assuming a field extension is algebraic. So an algebraic field extension is called simple if L is as a algebra over K generated by one element. It is a cyclic algebra and this X is called a generator of that algebra. So X is also called a primitive element of this Kx over K. Remember, there may be more than one primitive element that we will see. Primitive elements are not necessarily unique. It's exactly like a group. A group is called cyclic if there is a generator, and a generator of a group may not be unique, as you know from several examples. So simple extension is an algebraic extension. Right now I am assuming only algebraic. An algebraic extension is simple if it has a primitive element. And now I want to analyze in this example when can such an extension be Galois. So question is, we are going to analyze this question. So let me write it as an example. In this example we are analyzing when can a simple algebraic extension Kx over K be Galois. This is what I want to answer. Okay. Now this X is an algebraic element in this. So therefore remember our substitution homomorphism from the polynomial algebra to this. This is a substitution homomorphism. Any polynomial f going to f of x. And we are looking at the kernel of this. Kernel of this is definitely non-zero because since x is algebraic over K. So there is at least one non-zero polynomial in the kernel. So therefore kernel ideal is a non-zero ideal, and we know this is an ideal in the PID Kx that we know, which is a PID, and therefore generated by a single polynomial. And if we choose a monic generator, that monic generator is unique and that is called the minimal monic polynomial of x over K. So this is generated by mu x, where mu x is a polynomial in K, polynomial over K, monic, and it is monic with mu x on x is 0 a minimal polynomial, monic, minimal monic. So I will write once more. Mu x is the minimal, because it's unique, the minimal monic polynomial of x over k. And we know from the above that this kx mod mu x, this modulo the kernel, this is isomorphic to the image. Image is everything here because this map is surjective. So we have this isomorphism, and because this is a field, therefore mu x is a prime polynomial in kx. It is a maximal ideal. It generates a prime ideal. It generates a non-zero prime ideal. Mu x is a non-zero prime ideal in kx, and hence maximal also, and hence maximal. So the division algorithm will tell this is a field, and I am going to write down a basis of this. This is our field, this is our L. So obviously this we have seen earlier also, obviously 1x up to x power n minus 1, where n is the degree of mu, is a k basis of this field kx over k. So this in particular shows that we can compute the degree of the field extension. So this shows that degree field extension, degree of the extension equal to degree of the minimal monic polynomial of x. Now we want to compute the Galois group. Now take any see, I want to compute. So we want to know now how do we get automorphisms. And then we want to count also, and we want to say how many in which case they will be equal to the degree mu x. So this is very important observation which we will use again and again. And this observation is general. In this observation I need not assume that it is a simple extension. So I want to write this observation, a general observation, which is used very often in Galois theory. So let L over K be an algebraic extension. And let us take an element x in L and a polynomial f, in Kx. Then if I take any automorphism, such that polynomial f such that, so I want to assume also polynomial f such that f of x is 0. So this one also one writes x belong to VL of f. Remember our notation, VL of f is the set of all zeros of f inside the field L. This x may not be in K. So take such a thing. Then and let us take sigma. Then for every sigma, an element in the Galois group of L over K. So Galois group of L over sigma belonging to that means sigma is a K algebra homomorphism from L to L, K algebra homomorphism. So for every this, sigma of x is also 0 of f. This is what I want to prove. So what should I prove? I should prove that if I take f and evaluate at sigma x, it should be 0. So I want to prove that. So to prove that, I will write, to prove that f of sigma x is 0, then it will be a 0 of f in L also. So remember, f of x is 0 given to us. So f is a polynomial like this. Only once I have to write this, and this is again and again used. So it's a polynomial like this, a n x power n. Then what is f of x? F of x is given to be 0. That means I have to put small capital X equal to small x. So such a combination is 0 in L. Now I apply sigma to this equation. So sigma of 0, which is 0 obviously, because sigma is a group homomorphism from the additive groups. So this is sigma of fx. But then this is sigma of this sum. But the sum, the sigma respects sum, and sigma respect the scalar multiplication, and sigma also respect the multiplication. So therefore, when I want to apply sigma to this, I will apply separately plus, and sigma of a naught is a naught because sigma is k linear. On the elements of k it is same. The next one is sigma of this ax, but then a1x, but a1 will come out because it is k linear. So this is sigma x, a1 I will take it out, a1 sigma x, and so on. And the last term will be an will come out, and sigma x I will repeatedly take out. So this is nothing but sigma x power n. That is because it respects the multiplication. So we have used repeatedly sigma of x square equal to sigma x whole square. This is we have used again and again. So therefore, on the other side is this. So this is 0, but this is nothing but f evaluated at sigma x. So therefore, we have proved that f of sigma x is 0. That means we have proved that whenever x is in VL of f, then we have proved that sigma x is also in VL of f. So this simply means, this simply means, now let me get back to the, that means, see here we have L over K was a field extension, algebraic, and I have an element x here, and I had this L, and this we have this Galois group of L over K, and we have noted that this group operates on L in a natural way, but I have a smaller subset here now, VL of f. F is any polynomial. F is a polynomial in Kx. I have this 0 set of f in, so these are all elements x in L such that f of x is 0. Remember, it may not have all the zeros inside L. Given a polynomial f, it may not have all the zeros there unless that L where L contains all the zeros of F. But anyway, it doesn't matter. This set, this is a subset of L, and we have checked that this group operates on this, on the zero set of a polynomial, and this operation is nothing but a restriction of this operation. It's the same operation as it operates on L, the same operation VLF Galois group of L over K cross this to VLF. The map is the same map, evaluation map, sigma comma x, sigma comma y goes to sigma of y. We have checked that this is indeed an element here. So this is a finite set. L may not be finite, but this is a finite set. And if you assume your field extension is finite, then we also know this is a finite set. So therefore, combinatorial argument will help us to decide many things about field extension as well as the Galois group. So that is the trick. Now resuming back to our simple case, now assume your L is a simple extension and X is a primitive element. Then we have seen and X is algebraic over K. Then we have noted that this degree is nothing but the degree of the minimal polynomial of X over K. Mu X is monic polynomial in Kx, minimal monic. This we have just noted, X over K. And now we want to decide what is the Galois group and when can the equality happens. This, and when can the order be equal to exactly this. This is what I want to do. So look at mu x. This is a polynomial in Kx, and X is a zero of mu because it's a minimal monic polynomial of X. So I want to apply the general observation that we noted above, that this, if sigma is in the element of the Galois group, then if I apply any, so then you look at sigma of x, so that means sigma is a K algebra automorphism from Kx to Kx. This is sigma, K algebra automorphism. So x is here, then it goes to sigma x. But we have noted if this x is a zero of some polynomial, then this sigma x is a zero of the same polynomial. So therefore, by the observation, mu x of sigma x is also 0. So that means sigma x is another root. So that means that this, the zero set of mu x L, and it should also be an element in L. So if this is equal to say 1 0, we know that is x, let us call it x equal to x1, and let us call all other zeros to be x1 to xr. And we definitely know they are zeros of mu, therefore the number of zeros will not exceed the degree of mu, because we are over a polynomial over a field. So therefore what we noted that sigma will be uniquely determined by the zeros, because once you know the zero, so note that sigma is uniquely determined by any zero of, what I mean is, okay, zero uniquely determined by any zero of mu x, because if I know sigma is uniquely determined by, I should say, sigma of xi, where xi is any zero of mu. What does that mean? That means if I know, for example, if I know value of sigma on x, then I know all sigma, because our field is kx, but that is also same as kx1, because both have them the same minimal polynomial. So therefore these fields are equal. So therefore all that together, all together what we have done is, so I will write the result, that therefore sigma 1 is the identity, and sigma 2 means the one which map x to x2, sigma 3 the one which map x to x3, and sigma r is the one x which maps to xr. These are all automorphisms, because x has to go to some root. Where it can go to x2, it can go to x3, and so on. And I don't need this equality also, because all that I need is these are uniquely determined by their values on x only, because simply because L is kx, because this L equal to kx. If I know the value of any automorphism on x, then I know the whole automorphism, because this algebra L is generated by x. So therefore what we have proved is the Galois group of kx over k is precisely sigma 1, which is identity, because in this case x goes to x, then sigma 2, and so on, sigma r, as many as the number of zeros of the minimal polynomial of x inside the field kx. So therefore when can the equality, so therefore the order of the Galois group kx over k equal to this, which is the degree mu. This equality happens if and only if the cardinality of the zero set of mu x in L is precisely degree of mu. That means it has all the zeros are inside L and all are distinct. So all are simple zeros. So this is equivalent to saying, I will note it, and then, so this is if and only if all zeros of mu x are contained in L, and they are all simple, no repeated zero. Then only the equality can happen. Okay. Now these are two concepts. So this means, so I will write then, this is if and only if, that means mu x splits into linear factors in Lx. That is the meaning that all 0 lies inside L. That is the meaning of this. That is this part, and they are all simple, and they are all simple. That simply means, so that is mu x and the derivative mu x, they don't have any GCD, because if there is a GCD, that will be factor of mu, and therefore it will have a 0 in L, and mu x also will have a 0 in L. So, there will be common 0, and that will not be simple 0. So, this condition is also called, they are all simple. This condition can be restated as mu x is a separable polynomial. In Kx. That is the definition of separability. So, we will continue in the, so we know now when the simple extension is Galois. You only have to take the minimal polynomial and test whether all the zeros are inside that field and whether all the zeros are simple. And simplicity is tested without finding zeros, because we just have to find whether the derivative and this original polynomial have common 0 or not. Okay. Thank you. We will continue.